Hello everyone, welcome to Learning at 11th Hour. In this video, I'm going to be talking about flip-flops. So in my previous video, I would have shown you a lot about different kind of latches and how are latches different from flip-flops, right? So flip-flop is the clocked version of a latch. If you observe this configuration to the left over here, so this is basically the SR latch, and to it we are connecting a clock pulse. So the clock pulse is going to go into the S and R input through an AND gate, where the other input to the AND gates are the actual S and R that we are going to provide from the external inputs. So all this put together along with the clock pulse and the SR latch is called as the SR flip-flop. So this is represented as a box very similar to this representation with the S input, R input, Q and Q bar as the output, and a clock. So this is the SR flip-flop. Now I'm going to show you how we can obtain the characteristic equation for this flip-flop. So for that, let us first analyze the characteristic table of this flip-flop. So we know that whenever the clock pulse is going to be high, whatever changes are caused at the next state of the flip-flop due to changes in the input will be reflected or will be realized. So when the clock pulses are low, it's not going to happen, or at the level of a clock. So when I say clock, this is what I mean, a train of pulses. So whenever there is a rising edge that is encountered, and if the inputs change during the rising edge of the clock, only then the outputs will be visible. If the inputs change at any other instances, even then the output would be observed only at the rising edge of the clock, at the next clock pulse, provided till then the changed inputs hold their values. So that is why we call these as synchronous circuits, whereas latches are not synchronous, they are asynchronous. Whenever there is a change in the input, it is going to get reflected at the output in case of latches. So looking at this characteristic table of the SR flip-flop, it is very similar to the SR latch, practically no difference, only that instead of enable, we have the clock. And for every rising edge of the clock, we'll observe the changes at the output. So here we have no change for 0 0, 0 for 0 1, 1 for 1 0, and 1 1 is illegal because it leads to an indeterminate state at the output of the flip-flop. So having said that, I can actually elaborate this truth table. So let me assume that Qn is going to take up the values. Obviously it's going to take up the values either 0 or 1. So if it is 0, then I'll have a set of values for 0 0 0 1 1 0 1 1 at Qn plus 1, and for Qn equal to 1, we'll get another set of values, right? So let's write that out. If I say this is Qn, this is S, this is R, and this is going to be Qn plus 1. So when Qn is equal to 0, and the possible combinations of SR are 0 0 0 1 1 0, 1 1 is not going to be allowed, so I'll leave it as such. So I'll call it as a don't care rather. So for all of these cases, my Qn is considered to be 0, right? That's the previous state. Then what happens to the next state? According to this characteristic table, we can fill it up as 0, because previous state was 0, so next state will also remain 0 when the input of the SR flip-flop is 0 0. When it is 0 1, previous state is 0, next state will also remain 0 because the reset is high. In this case, Qn was 0, it will become 1 because set is high. So in this manner, I can write some more values over here. What would that be? That would be for Qn is equal to 1. So when Qn is high, again I can have 0 0 0 1 1 0 and 1 1 as very possible inputs to the SR flip-flop. So again, for no change, here I'll get 1 because previous state was 1, so next state will remain 1. Now when the reset is high, the previous state was 1, the next state will become 0 because the reset pin is high. For set, it will remain 1. The output will be set no matter what the input previous state was, right? And for 1, 1, it's don't care. I should ignore this input. So if I have a truth table like this, for this, I can draw a 3 variable Kmap. And using that, I can obtain the characteristic equation. So I have Qn, S, R. These are the inputs to this Kmap. 0 0 0 1 1 1 1 0. This is the gray code representation. And let me fill out the values here. This is 0 1 2 3 4 5 6 7, right? So I've numbered the minterms so that it's easy for us to plot the ones. So it is going to be for 0 1 0, so that means it is 2. So I'll place a 1 here. For 0 1 1, it is don't care. For 1 0 0, it is a 1. For 1 1 0 and 1 1 1, we have values. For 1 1 0, that is 6, there is a 1. For 1 1 1, this is a don't care. So this is the kind of Kmap that we've obtained. Now trying to group this, what do we get? So the first largest group that we see is this quad over here. So the expression for this quad is going to be uh, what is not changing, only column wise we can have S, because R is changing from 1 to 0, and row wise it is spanning over both the rows, and therefore Qn will change for the entire quad. So only S is consistent over here. I'll retain it. The next group can be formed by grouping this particular one along with this one. And the expression for this group turns out, so let's analyze the row. So row wise, this is going to be Qn. And looking at the columns, these two are the columns that are going to be analyzed right now, because that's where our group is spanning, this pair is spanning. And over here, R is 0 for this column and this column. Therefore, since it's 0, I'm going to retain it as R dash. Now, putting together the expression for both the groups, the expression for the next state, Qn plus 1, right? Qn plus 1 for the SR flip-flop is going to be S plus Qn R dash. So this is the characteristic equation of the SR flip-flop. Let's move on to JK flip-flop and try to obtain the characteristic equation. So looking at the characteristic table of the JK flip-flop, we see that the issue of 1 1 of the SR flip-flop has been addressed over here, because the feedback from the SR latch goes into the AND gate along with the J input and a clock. And the presence of this clock makes this a JK flip-flop. So putting all of this together, here we have the JK flip-flop, where this is the J input, this is the K input, this is the clock input, this is being Q and Q bar. So representing it, we can actually obtain it as a rectangle with clock, J and K input, Q and Q bar being the output. It is important to note that for the JK flip-flop with this symbol, or for any flip-flop for that matter with this kink kind of a symbol which represents the clock, if there is no bubble over here, it means it is positive edge triggered. And if there is a bubble over here, this represents negative edge triggered. Now, since all the clocks are pointing upwards, we are just looking at positive edge triggered clocks. So I'm going to remove this bubble from this flip-flop and make it represent a positive edge triggered flip-flop. So now, since the truth table is very similar to that of the SR, So let me try and make changes from this truth table itself to obtain the table for the JK flip-flop. So here we see that our inputs are going to be different. It's going to be J and K, and the output in case of 1 1 is going to be different. So how is it different, right? So here let's update this table here. This is JK, and for 0 0 it is no change as shown over here. For 0 1 it is reset for both the cases. For 1 0 it is set for both the cases. That is the cases here, I mean Qn is 0 for one case and 1 for one case, and the last one is toggle. So if Qn is 0 and Jk is 1 1, it's going to be 1 for Qn plus 1, and if Qn is 1 and Jk is 1 1, it's going to be 0 for Qn plus 1. So this is ultimately the truth table that we get for the JK flip-flop. So from this we can obtain the Kmap. Again, it's going to be a three variable Kmap where Qn, J and K are the three inputs. So we have Qn here, JK here, 0 0 0 1 1 1 1 0, and we can mark the minterms 0 1 2 3 4 5 6 and 7. Now where do we place the ones? At 2, 3, 4 and 6. So 2, 3, 4, 6. So this is where we get our minterms. So having got this, let's try to group it. So here I can clearly see that this is one group and this is also one group. So let me try to find, now since all the ones are already covered, if I try to group this pair also, both the ones have been taken up by one of the groups formed. So if I form another group using already covered ones, then it would lead to redundant term in the expression. Even without that term, the circuit will work just fine. So if the ones are already covered, no need to group it one more time. So let's just go ahead and obtain the expression for these groups. Looking at this particular group, it's along the row, so Qn, because it's 1 for both of these, and along the columns when we analyze, here we see that J is 0 for this column and it is 1 for this particular column. So, and K remains 0 for both. So, it is K dash when it comes into the expression. Now, the expression for this particular group, it is Qn dash because it's along this row. And looking at the two columns over here, only J remains 1 for both of these ones in the group. So therefore J is going to be in the expression. Now putting the two together, the characteristic equation therefore can be written as Qn plus 1 is equal to J Qn dash plus K dash Qn. So this is the characteristic equation for the JK flip-flop that is positive edge triggered. Moving on to the next one, this is the D flip-flop formed with the help of the SR latch gated with the clock pulse, and the D input is provided directly to the AND gate connected to the S input of the SR latch, and inverted version is given to the second AND gate connected to the R input of the SR latch. So this is the characteristic table of this flip-flop, right? So we are using the latch connecting the clock, put together this entire configuration becomes a flip-flop. So this is the D flip-flop. So no matter what D is, if clock is 0, one of the inputs of these AND gates is 0, so no output, the output of these AND gates will obviously be 0. So therefore no matter what the um, D input is, if clock is low, both the inputs to the SR latch is 0 0. If the inputs to the SR latch is 0 0, it means that there is going to be no change at the output, as per the characteristic table of the SR latch. That is why they have kept it as Qn. Now, if the clock is made high, so at the positive edge of the clock, if D input is 0, then the next state is 0. Next state. So after one clock pulse, we will see the change in the input reflected at the output with a delay of one clock pulse, right? Again, for D equal to 1, the next state will become 1. So we can write the truth table for this in this manner. If I take the two inputs as Qn and D. So say Qn is 0, D is 0, 0, 1, 1, 0 and 1, 1. These are the possible combinations. So what would my next state be? I can fill this up with the help of this characteristic table. So I'm going to consider that my clock is always high, right? So I'm not considering this as a specific input as such. I'm assuming that the clock is going to be high. So in that case, uh, the next state is going to be whatever my D input is, right? If you look at the characteristic table also, when the clock is high, the next state is nothing but whatever my D is. So I can just directly fill it up, and the very simple characteristic equation and the obvious one that we can obtain is Qn plus 1 is equal to D. So this is the characteristic equation of the D flip-flop. Now let's move on to the T flip-flop, the last one. Over here, the characteristic table can be represented in this manner. So for T equal to 0, the previous state is going to be the next state. For T equal to 1, the next state is going to be the toggled version of the previous state. So if I am going to write the expanded version of this, so Qn and T are going to be the two variables on which the next state is going to depend. So the previous state and the present input, right? So 0, 0, 0, 1, 1, 0 and 1, 1. So what would Qn plus 1 be? So since T is 0 over here and here, whatever my Qn is will be retained at Qn plus 1. So I can write it as 0 itself in this case. And in the next case, I can write it as 1. So this is because the T input over here for both the cases is 0. Now, whenever T is 1, whatever Qn is, the next state is going to be the complement of that. So in this case, it is going to be 1, and in this case, it's going to be 0. Having said this, looking at this truth table, this is actually the truth table for the XOR gate. Therefore, we can say that Qn plus 1 for the T flip-flop is the XOR of T and the previous state, Qn. So that's all with today's video. I hope how we arrive at the characteristic equation for each of these flip-flops is clear to you all. If there are any queries or suggestions, please do feel free to post it in the comments below. Thanks a lot for watching.